Okay, it is students, it's very easy to find out the uh, experimental ratio. That we do it from the spectra. Supposing there were two peaks which we had seen before, so we can, here for example, this peak is at higher energy, this divided by this lower energy peak, that gives us the experimental value. Okay, and in this case the experimental value which comes was E2 divided by this, and the value comes 1.7. Okay, for this value, when we go to the table mu2, okay, here it is. Okay, what we get is, okay, the value of delta octahedral over B is equal to 10 is this, and the value of E1 over B is equal to 10 also. Value of E2 over B is 16.7. Okay, so what we do here is now that add delta octave equal to 10 given here. The value of E1 over B, E1 over B is equal to 10. We can see that E1 over B is equal to 10. And of E2 over B is 16.5. And here is that E2 over B is 16.5. I want to show you from the actual graph. Okay, at delta octave, this is the D3. Okay. Okay, and we go this way, and this is 16.5. We go from here, we go up, it touches here, and we come here, it is 16.5. Okay, this is the second transition. Okay, from where we have come. So, see table 2. I have shown you all the energy of the first transition was 8, and third the value of E1 energy 800 as you in equation 1. Okay, so B is equal to E1 over 10. We can put value here of the E1 which is given this one. So the value of B will naturally come like this. 8,000 reciprocal centimeter divided by 10 is equal to 8. So B is equal to, we can find the value of B again with the help of E2 over B. Value of E2 over B is 16.5. See table 2. Okay, this value is at delta octahedral equal to this value is at delta octahedral B equal to 10, where E2 over B is equal to 62. So B is now equal to E2 over 16. The value of E2 is equal to 1316. So this divided by that will give you this. Average value we can calculate, this will come like this. So the next thing which we want to determine is value of the ligand field parameter, that is delta octahedral or DQ value. Okay, this is extremely easy. Okay, we have found out the value of delta octahedral, that is equal to 10. So what do we want to find out? We want to find out, if we know this value, we can find out. This value has already been calculated. So multiply this with value of B and you get that. And this is what I have done. Okay? Just insert the value and you can get that. This is important. This is a prediction of the third band. How do we do it? Okay, for this you have to consult the Tanabe-Sugano diagram. Value of what? Delta octa will be, okay, and at this value, E3 over B, see this scale, E over B scale on Tanabe-Sugano. So this is what you have. So from delta octet over D equal to 10, we go up. We go up. Where we want to go? We want to go to the third transition. That will give us mu3, the third band. So 10, we go up like this. Here it is. Here it is. And it is touching it. 10 is touching here. Okay? And you can see there we have written 28.5. It comes at 28. Okay, you can verify it yourself. Make a left, this is 28.5. Okay, so we find out this value. So next thing, this band is not visible, as I have said, it is hid under the charge transfer. So value of mu3, which is this, A to G to T1G, A to G to T1G, yeah, here at this. The third band is equal to 23.1.42. It is calculated here, okay. E3 will be 28 multiplied by B, which is equal to this, will give you this. This is the third band. So we find out this again, and you can find out determination of percentage covalent character. That is very easy. Okay, percentage covalent character is given by B over B naught. B is Rocca parameter and B naught is Rocca parameter value for the free ion. It's given. Okay. Now in this case, this value is given equal to 1030 reciprocal centimeter. We know this. This is given, and then whatever value will come, that is the percentage ionic character. Okay, it is done here. B over B naught, okay, multiplied by 100 will give you the percentage ionic character. That is 812 is the value of B divided by B naught value 1030 reciprocal centimeter multiplied by 100. That comes out to be this. So covalent character is 100 minus this, that will be this. Okay, now this has been a rather hit and trial method for determination of all these things. There is another easy method available for determination of delta octahedral over B. So it is easy, you will understand it very easily. So let me discuss it that. Usually we have transition energy ratio diagrams. Transition energy ratio means E2 over E1. Okay, these are transitional, or E3 over E1, or E2, E3 over E2. These are, now you see that I have written there, mu2 over mu1. Okay, means E2 over E1. It is plotted against delta octahedral over B. I will show you another diagram in a minute, but this is for the D2 system. This is for D3 system. These energy ratios plots are given in the books. So we will see how we use them. Here it is. See this one. Then I will go back and explain you how we do it. I have plotted mu2 over mu1. This energy ratio is experimental from spectra. This band high energy divided by this band energy. So you get this. If you know this experiment, then what you do is you have this, I supposing the value of this is 1.8. So what is the value? From here you go this way, we come down. Whatever is the value here, that is the delta octahedral value. I think I have done it with the help of some examples. So let me do those examples. Okay. On page 8, a previous lecture, please. This is important. Okay, whatever was done there, okay, for finding out delta octahedral B in previous lecture, I have just taken that. We found out in that example, you can go back and see my previous lecture, lecture 14. We found out delta octahedral was equal to 14 after going through a very rigorous process. Okay, 24. For this value, okay, the energy ratio was 1.59. Okay, this was the experimental value. So if this is the energy ratio, we found out the delta octahedral will be this. Okay, fair enough. Now I think I want to do this with the A. I have explained this how we do it. Let me explain to you here. 1.59. This is for previous okay lecture. Okay, 1.59 is the experimental value of energy ratio. So here is the energy ratio diagram. See, this is D2, not D3, D4. I have taken that, and it says experimental value is 1 point. Okay, come here. This is 1.59. This is 1.6. This is 1.4. So what I do? I take this value. From here I make a left parallel to x-axis. And it touches this curve C. Where? At x point. From x point I go vertically downward. Wherever it touches, it is so easy. That is the value of delta octahedral. So they found out after a very tedious, difficult way, hit and trial 24. We do it hardly in 1 minute. 1.59 experimental. Go this way, come down, this is the value. Okay, now I'm going to explain it with the example. Here is an example. Vanadium complex shows two prominent peaks, one at here and the other at 26, 200. What is the value of delta? Simple, very simple. Okay, note, once you find out the value of delta, you can easily determine the rest of things. What are the rest of the things? Rest of how you will find value of ligand field parameters, how you find percentage character, how you find this, how you find this. All you need to do is we find out this value. So answer to the question which I made, okay, what is the value of delta? Its experimental value. When you divide this with this, okay, you get 1.59. Now, just come here on this plot, 1.59, and starting from this, only on the axis, the values, okay, draw a line parallel to x-axis, go up to the curve C, and then go vertically to downward as I explained. So it touches at 24. So that's to be found, finished. Example 2, vanadium has an absorption band at this and this. Using energy ratio diagram, determine delta octahedral. Answer, we will use D2 diagram because this is a D2 system. So the energy ratio, or the experimental value here is now 1 point, this divided by this is 1.49. It is not 1.59. It's a different complex, different spectra, different values, and so it is this. Now starting from point 1.44, here it is. You will take what? D2, 1.4. Make a right turn. Touches it somewhere here. I have put a, you see, braces along it. Okay, it touches it here. Go vertical. This value is 31. So it is that easy thing. Okay, where it touches values. So delta octave. So copied from another literature source, example 2 exercises is solved with another D2 energy ratio diagram. Here is the energy ratio diagram. Okay, I have taken it from some other source. Again, what he did was he took it 1.4, okay, and this is 1.44, go right, come down, and this is 31, the same thing. He did it with the other method also, E over 1 over B, etc. Example 3 I'm giving. Chromium metal complex shows two strong peaks, one here and the other here. Determine the answer. We will use D3 energy level. Why? Because chromium 3 is D3 system, not D2. The previous examples were D2. So we know the experimental energy ratio, that is 1.7. So the rest of things should be easy if we have D3 diagram. Okay, D3 diagram. Here is D3 diagram. This is energy ratio diagram. And what was the value? 1.7, I think it's there. So I go and find it out. And then I go here. It touches here at X. Come down, vertical downward. And it touches it here. So this value, delta octahedral, would be is equal to 7. Okay? In this case, it touches at 7, is 7. The rest of the things we can do. And this is the end of the lecture 15 notes. Thank you very much for your patience. These are very important lectures. Okay? So please try to do it yourself. Okay? Keep the notes in front of you and find out whatever table I have constructed. You should do that yourself. But then with the help of diagram, it will solve the problem. God bless you, everybody.